Okay, we can begin our next workshop section. Fundamentals in Optics for Biophotonics by Dr. Hector Hugo Cerezo Núñez is from Applied Optics Laboratory, Physics Faculty, Universidad Veracruzana de Mexico. A brief introduction of Dr. Hector. Dr. Hugo Cerezo Núñez obtained his PhD in optics from National Institute of Astrophysics, Optics and Electronics, Puebla, Mexico. He had a postdoctoral position in 2002 at the Center for Photonics Technology, Blacksburg, USA. He is now a tenured full professor and co-founder of the Applied Optics Laboratory at the Physics Faculty, Universidad Veracruzana, Jalapa, Veracruz, Mexico. His recent work has utilized optical fiber to trap and manipulate matter, and also is involved with optical fiber sensor, biophotonics, and optical metrology topics. He is also a member of Optical SPY in Mexican Academy of Optics. So please go ahead, Doctor.
Thank you very much. Thank you, Mr. Chairman. Well, I don't know if it's necessary to use the microphone. Okay, I prefer this way. It's okay. No, but
I can speak.
yeah, I can speak. Yeah, no, I don't know. Thank you. Don't break also. Okay, good afternoon. Thank you very much to be here. Well, what's going on?
Sí, está conectado aquí.
Well, this workshop is planned to in a basic level. So please, I ask by budget physics because probably all this information I am going to show you is a basic course of physics, but I'm going to try to do emphasis in biophysics. Well, that is the proposal. So the topic of this event is related to trends in electronics and health informatics. So why we have to hear about fundamental in optics? Well, since my point of view, it's very important to relate electronics and also informatics with optics. As you know, optoelectronics is involved with photodetectors and light sources. So that is the reason because I think it should be important. Also because data analysis such as regressions and classification are used in optics also. And at this moment, there's a large quantity of data that should be analyzed. So that is another reason because we need to relate optics with these topics. Well, biophotonics, in this case, all that devices and data analysis is related with information taken from biology or medicine. So that is that should be reasons because we need to hear something about optics. Okay, for to start, I need to draw something. Probably we know about light, isn't it? In general, we can say that light can be described as a strike, as a wave, or as a particle. In this case, let me show you, let me draw something general about light. This is like a ray, like a wave. Or maybe we can use this like a photon or like a pulse. That is in general the behavior that light has. In general, there are two representations for light. To start, we need to recall what is light. Well, light is, we can find that light is defined as a very small part of electromagnetic wave. Usually, this part of the electromagnetic radiation, electromagnetic radiation, usually it is located in the middle of the whole electromagnetic spectrum. In one side of this light spectrum, we can find infrared radiation, microwave, and radio waves. And in the other side, closer to blue light, we can find ultraviolet, X-rays, and gamma rays. So the characteristic for all this kind of radiation is the wavelength and the frequency. So for the case of light, as it is defined, light is defined based in the radiation that our eyes can detect. But it's part of all the electromagnetic radiation. So, and this visible part of the electromagnetic spectrum was defined, as I mentioned, because our eyes detect that part of the electromagnetic spectrum. That part of the electromagnetic spectrum comes from 400 nanometers to 700 nanometers. And our eyes has a very high sensitivity, around 555 nanometers. That means the green color, the green light. On one side we have blue light, and in the opposite side of this sensitivity curve we have red light. So this is our first example of how optics, or in this case, how light is related with biophotonics. For our case, we have two powerful detectors of electromagnetic radiation. In this case, we have the two detectors for visible light. Okay. Well, it's important. I'm sorry because I didn't have more time to translate this to English, but I want to explain as much as I can. Okay, the first thing then is that we have to identify that light is the phenomenon, the physical phenomenon, and optics is that part of the physics that deals with the research application of light. So we need to remember that we have two different things. Okay. And as I mentioned at the beginning, there are basically two general moments, but there are different representations to describe the light. There are basic representations and more complex representations. The basic representation of light is like a ray or has a wave. That representations are mainly qualitative and are mainly scalar. But there is another kind of representation for light that is electromagnetic, has an electromagnetic wave. In this case, we can represent the light has a vector, not only has a scalar parameter. And finally, we can analyze the light in a quantum way, as a quantum optics. In principle, if you use quantum optics, you can describe all the phenomena in light. But this should be a very complex tool to analyze some phenomena, some phenomena that could be described more easily if we use ray or if we use wave. Okay. Well, now we have passed a kind of introduction. And now we are going to talk a little bit more about the first representation of light. In this case, is as a ray or as a wave. we can represent in a basic manner the light. Consider some parameters, some basic parameters of light. For example, we need to consider the speed of light. What is related with the speed of light? Well, it is considered that the speed of light in the vacuum is the maximum speed that light can reach. In any other medium, like a gas, like a liquid, or like a solid, the speed of light will decrease. This is happening in the nature, so we can avoid that. So if that is the case, it's convenient to define a parameter that compares to compare the speed of light in the vacuum and the speed of light in any other medium. In this case, we define the refractive index. Okay. If we establish this definition, we can find that in the vacuum, the refractive index should be 1, and in any other medium, the refractive index should be over 1. Okay. Well, but in many cases, it's very difficult to measure the speed of light. If we take in account this definition, we can measure if we know the refractive index in a medium, we can find the speed, or we can estimate the speed of light in that medium. So it's experimentally, it's more easy to get the refractive index, and with that we can establish what is the speed of light in that medium. So this parameter and these relations are very important, because we need to consider that the light is not going to travel in the same way in different mediums. Here, I am going to show you a picture of the effect of a beam when it passes through a bulk, a piece of glass, or maybe a piece of acrylic. So you can see that when the light passes through this medium over this interface, the beam of light change the path, and when the light this beam goes out from this piece of glass or piece of acrylic, the beam recovers the initial path. So here we can see that for example, if we use as a reference a normal, imaginary line here, a normal, we can see that angle of incidence with respect with that normal is not the same that the angle when the light is refracted. So that is an effect of the change of the speed from the air to a different medium. That air. Also, we can observe, well, maybe not in this picture, but we can observe a very small change in the color. That change in color of the beam inside the medium is related with the change of the speed of light in that medium. Okay, and in this table, no, in this list, sorry, in this list, we can observe different values of the refractive index when we send a beam, for example, like this beam, in different mediums. For example, if we launch or if we propagate a beam in different gases or liquids or solids, we observe different refractive index, as you can see in this list. So you can see that the refractive index is increasing as the medium is optically more dense. That means that the speed of light is decreasing. In this case, around the order of this list. That means, for example, that the light that beam in a solid should have less speed that or is traveling slowly than in a gas, for example. Okay. So another important thing to understand the basic propagation or the basis on light is a Fermat's principle. What means the Fermat principle? The Fermat principle, let me write this here. Okay, what does it mean? What does that mean? Fermat principles say that the light should travel along a trajectory that takes the less time to travel from one point to another point. That is very important also. That is something very important to consider about light. And also that sometimes that path in the light is not only one. Should be and sometimes should be many paths to reach from one point to another point. So that is in general the Fermat's principle that established the Fermat's principle. And there is another principle, very important principle to describe the propagation of light in a basic way. That is the Huygens principle. This principle is qualitative, and this established that if we know an initial perturbation that describes the light, after some time and after some distance, we can stimulate the medium where the light is propagating, and that stimulation conforms the next sources of light. And that is a qualitative description of how the light can be described in the propagation. And for example, in this picture, we can see the relation between the rays. We can describe the light as a ray and as a wave. We can describe in both manners and are related, and should be related with the Fermat principle and the Huygens principle. Well, two more things to consider at the beginning of or in the basic description of light. And one is the reflection, and another one is the refraction. Reflection of light and refraction of light are are involved in two laws. In this case, a law that relates the manner of how a beam is reflected over the interface, and the other law relates the manner of how a beam is transmitted into the medium. For this case, the reflection law established that but first we need to see how to describe the law. Okay. In this case, we need to consider a flat interface, and we need to consider a point when a beam comes or propagates to the other medium. In that point, we need to consider a normal line. That normal is a reference to measure the incident angle, the reflected angle, and the transmitted angle, as you can see in this diagram. So in this diagram, we have to consider the initial, the incident angle, the reflected angle, and the refracted angle, as I mentioned before. In this case, the reflection laws establish that the reflected angle, or the reflected angle is equal in the value to the initial angle. And in the case of the beam that is propagated in another medium, the relation between the angles is not the same as in the reflection law. It's given by this relation, where is related the incident angle, the refracted angle, and two refractive index. The index of the initial medium and the index of the refractive index of the medium where light propagates. So we can say that these considerations, all these considerations, maybe refractive index, Fermat principle, Funke principles, and this reflection and refraction are ideal, but it works when we start to study the interaction of light with the matter. So it's very important. Even it is ideal, it's very important to consider the behavior in that way. About reflection, we have a special case. In this case, is a total internal reflection. What does that mean? This means that the light has a different behavior when it travels from a medium of refractive index higher than the other medium. For example, where light continues traveling. So in this case, if we launch light from, for example, from glass to air over an interface, we can observe that when we are increasing the incident angle of the beams, we are going to find a case or a point, or how can I say, a case where the refracted light is not in this medium. The refracted light lies over the surface or the interface. If we continue increasing the incident angle, we observe that all light is into this medium. That is a total internal reflection, and that angle where this phenomenon appears, we call critical angle. And that critical angle is also related with the rate between the refractive index of one medium, the incident medium, and the other medium, the medium where the light continuous travel. And this principle is also very important in many applications, in many devices, and it should be considered in the direction again of light with matter. Okay, now let me show you some examples of light propagation considering rays or beams in some basic optical elements. Well, this beautiful picture is an old picture that I take from a book. I don't remember the name of the book, but I can share with you later. Here we can see that, for example, a lamp can be converted or can be transformed in different beams. So we can transform a candle or something like that in different beams, or we can select different beams, and then we can launch that beams over different devices, basic devices. Well, but maybe it's not necessary now because we can use a laser like this. Okay. In this picture, we have the representation of how we can see the reflection of a beam over a very polished surface. This case is to represent the specular reflection. And in this case, we have the same beam, but it's launched over a not polished surface, like this, for example. This should be a mirror, for example, and this surface should be, for example, a piece of material like that. So in this case, we have specular reflection, and in this case, we have diffuse reflection. So this basic phenomena is something that also we have to consider in biophotonics, because our skin doesn't reflect in this manner, it reflects in a diffuse way manner. Okay, so as I mentioned, that this is something basic, but probably is something that we have to consider. Here we can see the behavior of beams when they are launched over a mirror. This is a concave mirror, and this is a convex mirror. We can see that beams tends to be reflected, but in this way. I'm not sure if this is. In the first case, we have a convex mirror, and we can see three beams that are inside that are coming to the surface. So the surface reflects in this way, this manner. And in the second picture, we have a concave mirror where the beams inside in this form, and the light is reflected, trying to be in one point. This case is this point. So the behavior of the light is not the same in different surfaces. Also, you can see, we can see, I'm sorry, we can see the different behavior, different elements, like that. Okay, in many optical instruments, we use lenses. And this is an example of how beams can travel through a lens. In this case, it's a positive lens. In both pictures, we have a positive lens. So we can see how beams are trying to focus in one point. So this is very schematic, but beams and waves can be used to describe the behavior of the light in that very basic element, optical element. In the case of optical design, this kind of beams and consideration are used to calculate or to simulate a more complex optical device, optical instruments. Okay. Well, another important thing is that we can describe mirrors and lens in only one equation. And the more a simplified equation is this one or this one. That equation is related with the thin lens. It's obtained from the consideration consideration of thin lens, not big lens, very thin lens. And it's useful to describe also mirrors. That equation can describe lenses and mirrors in a basic description. And we can put this equation in this form. If we compare the distance of the object, in a few moments I will show how is that the distance of the object with the focal distance and the image of the object, and the image in the device with the focal distance. Okay. We have to remember what is in the case of a lens, for example, a simple lens, we have to remember that we have, for example, an object that usually has a distance from the object to the lens. And we have an image of that object, an image that is created by this lens, and we have a distance. We have to describe a distance of this image. And something that is a characteristic of the lens in this case is the focal distance. In this case, we can describe a focal distance. For example, I don't know, for example, here. For example, this lens should have this focal length. That means that it's not necessarily have to be not necessarily should be the same that the distance of the image or should be the same that the distance of the object. So in this case, this equation is useful because if you know the distance of the object, you can, and if you know the characteristic of the lens, you can know the image, the distance of the image, or in a different manner. Okay, and how to use this equation? I mean, how to take +1 or -1? Well, it depends if you previously know if you are using a positive lens or a concave mirror or something like that. You have to know purely how is the device. But with that equation, we can obtain different conditions or different situations or different relations between the object and the image for one device, in this case, for a concave mirror or for a convergent lens. We have different situations where we can observe real objects, virtual objects, real images, virtual images, and so on. This other plot that are the situations for different convex mirrors or different divergent lenses. So with only that equation, you can obtain the different situations. But this is only approximation. Remember, this is not something more real, but it's very useful. Okay. Well, you can also estimate the distortion not only in the size of the image compared with the size of the object. You can also obtain the distortion of the if the image is very thin or is broad. Yeah. Okay. Here there are another graphical examples of light propagation considering rays or beams, but now in some basic optical instruments. So if we know some parameters or some definition, some basic definition with light of the behavior of light, we can understand how to describe a basic optical instrument. For example, the eye. You can understand and you can see how light is focused on the retina, or we can explain or understand in a basic manner how our eyes has some problems. For example, myopia. Is it correct, myopia? Okay.
Actually, now you're working on this. Have you ever seen some work talking about like why the brain cannot correct myopia by itself?
Mhm.
Because we use glasses. I use glasses. Many people use glasses, right? And the brain has plasticity, and it's very good to correct things, but it goes into light coming to the eye. Seems like it cannot do it. And probably because this is a condition, a very recent condition in humans. This condition, the myopia. So have you ever read some?
No. But I think it's not a simpler answer.
No.
Because it's not only why the light is not focused here. Maybe it's because the response of the or the cells in the retina. I mean, I think it's something more complex. I don't know.
No, it's just because we're working on this right now. If you are aware of some work.
No, but I haven't. Sorry. Okay. Also, we can understand, for example, the principle of a camera. The camera we have in the cellulars. Also, we can describe or understand how a magnifier works, or an overhead projector. We don't use anymore overhead projectors, but we can understand how we can project an image from a transparent slide. Also, we can understand how a microscope works, or even more, a telescope, and so on. So you can understand with basic principles. You can understand the propagation of light in some of these optical instruments. Okay. Let's see what time is it? Okay. 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 Let me continue a few minutes more. And another description that I would like to discuss a little bit is about the electromagnetic representation of light. Okay. In many cases, we can describe some familiar phenomena of very common phenomena with drag and weight, but in that case, we only have an approximation of what is happening. But if now we take in account that the light is an electromagnetic wave, it can be described as an electromagnetic wave. If we do that, we can describe some phenomena that we cannot describe with ray and waves. For example, polarization of light. We need to use a vector representation of light. In this case, we have to use the electromagnetic representation. And as we recall, electromagnetic wave is composed by two fields. One is the electric field, and the other one is the magnetic field. That cartoon is a representation of electromagnetic wave in the background, yeah? Where there is no distortion, and the propagation is beautiful. It's continuous. Well, if we analyze the electromagnetic wave, we can see that there is a fierce vector that initially we don't have, and that vector is the Poynting's vector. How we can understand the Poynting's vector? Okay, Poynting's vector describes. I'm sorry, but I have to jump. Describes how the energy of an electromagnetic waves propagates. If we analyze the propagation of the electromagnetic wave in the space, we are going to conclude that there is a quantity of energy by unity of time that passes through an area. And that is related with the two electromagnetic fields. This means the electric and magnetic field. So, and we can conclude that this relation, or even in this case, this relation between the two vectors should be related with this third vector. In this case, is the pointing vector. And the physical description of the pointing vector is, as I mentioned, that it has energy by, or it carries energy by unity of time passing through an area. So that is the meaning of this pointing vector. And that's very important because it says that the energy is propagating in that direction. Okay, we can see that the pointing vector is in this case, for example, should be in this direction. So here we have S. But the electromagnetic waves oscillates to a very high speed. So you can detect the magnitude of the pointing vector. You have to have an average in time in order to know the value of that energy. So if you have an average in time, you can obtain the density of flux or density of radiant. I don't know how to translate. Density of flux, radiant flux, density of radiant flux. Yeah. So in this case, this is the parameter that we can measure in the laboratory. Not the magnitude of the pointing vector. Is the average in time. Okay. And from here, if we know that we have that an electromagnetic wave carries energy, we can find that that energy should be associated or should be transferred as a linear momentum, even more as a pressure, or even more as a radiation force. And that relation, we can see that relation here. Let me show. For example, we can relate the energy transmitted by the electromagnetic wave divided by the speed of light with a linear moment. So the linear moment, or the transference of energy to a linear moment is by this relationship. And the relationship between the electromagnetic wave, the energy of the electromagnetic wave, and the radiation pressure is by this relationship. Or if we are doing something classical, we can associate that density, flux of density of the electromagnetic wave with an induced force. In this case, we have to know the area where the radiation is incident. Well, taking in account that now scientists can understand, for example, the form that has that kind of explosion in the space, or in part can explain the way how, as we can see, a comet. But in our case, in the case of biophotonics, this force, this induced moment, can be used to push microparticles, organic and inorganic microparticles, or even more to catch catch or to push microparticles. So even the force the induced force is very small. You can use this to move microparticles. This is a beautiful representation of the forces involved in an optical trap. Here we can see that there is not only one kind of force involved, but we have radiation pressure, or radiation pressure, and something called gradient force, and they have different descriptions, and that representation shows how you can trap a microparticle in a microscope level. When do you think we have a break? But first, if you have any question, I can answer, and we can continue after the break. I don't know.
Yes, we are in time. Is there any questions? No. Any questions in this first part? Well, if there is no question, then we can have a small break, like for tea break, 15 minutes. So we can come like 4:50.
Sí, dice la doctora que sí. No necesitamos. No sé, se han de haber tenido algún micrófono y agregamos y lo dejamos así con un micrófono. Sí, pero si alguien se va a comer, pero creo hacer las preguntas que se van a tener que hacer cada uno, ¿no? Si alguien sí.
¿Sí se escucha bien?
Sí. Sí, pregunté en internet. Los que están en internet, en YouTube y en Zoom, se escucha.
Ah, perfecto.
Se escucha bien.
Gracias.
Sí.
Bueno, yo tengo una pequeña duda.
Sí.
Al principio había mostrado algo del espectro o
Ajá.
de lo que nosotros podemos ver con nuestros ojos.
Sí.
¿Por qué el pico está en el verde?
Ah, eso tiene que ver con la evolución, con la adaptación que tuvieron los seres humanos al medio ambiente. Eso tuvo que ver.
Es que estaba viendo por ahí de por qué todas las plantas, por qué en general las
Claro.
hojas son verdes, ¿no?
Sí.
Y creo que tiene que ver con que digamos, el pico de lo que emite el sol, creo, está en el verde también. Entonces refleja, creo, la luz de mayor intensidad y por eso.
No. El pico de emisión del sol no está en el verde, no.
Está aquí en el...
Ay, no te traje una gráfica, pero no está en el verde. No.
Okay, so we continue the workshop section 2 in the same this way.
Thank you, Mr. Chairman.
Okay, well, please remember that all I am talking about is to think about the interaction of light with matter. In this case, we can consider that interaction of radiation should be also in organic matter. That means plants, animals, cells, organic material matter. So at this moment, we know that the electromagnetic wave or this representation of light can induce a linear momentum. Pressure or the radiation pressure also can induce a force. So for me, this is the most important part of in the interaction of light and matter, because now we can observe the results of all that these phenomena that we can find in an electromagnetic way. And what should be some consequences of this interaction? Well, we now know that the speed of light can change when it passes through a different mediums. Also, that the light can change the direction. I mean, if initially has a path, when it is inside another in a different medium, the direction can change, and that is very important because we can use that to measure something. Also, light can induce a kind of resonance, or the light itself can have a resonance inside that medium. Also, we can observe a change of energy or conversion of energy. Energy can be transformed. The initial radiation, the energy of the initial radiation can transform in another kind of energy. Also, the radiation can be absorbed, or even more, the radiation can change in a specific direction, initial direction. That's mean polarization. And this cartoon try to show some of that effects. In this case, we can observe that when light is into a different medium than the initial, we know that we have reflection, transmission, but also we can observe absorption, or even more, scattering, or change of energy, like luminescence, fluorescence. Okay. Here, we can see two more cartoons where the representation is not like that. It's a little bit more realistic. In this case, the reflection is in a direction different from the initial direction, and the transmission, we can observe that the refracted beam. Also, we can represent the scattering and the absorption. The other cartoon is in the same description. Well, but if we consider non-homogeneous medium, for example, we consider an inhomogeneous medium, such as addition, the behavior of light in that medium is more complex. It's not so easy as you have reflection and refraction, and that is more complex. This scheme tries to show how light propagates inside an inhomogeneous medium in a complicated path That is a kind of Monte Carlo simulation in addition. And here we can represent several of these effects, scattering, and how light is transmitted. Well, we are going to discuss a little bit more some of that effects. Okay, let's start with the speed of light. We have discussed that the speed of light is going to change when we pass to another medium. We are going to discuss more about that. Now we are going to discuss the chromatic dispersion. What does that mean? That is related with the change of the speed of the light. But remember, we defined the refractive index has a rate between two speed of light. Well, we can represent that refractive index in terms of the wavelength. From here, we can observe that the refractive index is going to depend of the wavelength. What does that mean? That different colors in a material is not going to travel with the same speed. This famous picture that studies many years ago by was studied by many years ago by Newton, try to explain that dependence of the refractive index and the wavelength. Well, I have I don't think we can see the dispersion, but anyway, I have a small prism. So if we launch light through a prism, we are going to observe different colors. That means that first, that the light, white light is composed by different wavelengths. And the second one is that the way of how that colors spread is related with the speed that they have into the medium. For example, the red color or the wavelength associated with red means that inside that medium, the red light travels faster than the blue or violet light. That spread in colors refers to the dependence of the wavelength. Refers to the dependence of the material of the wavelength. Okay. Oh, here, something we can see that. You can see we are using the white light of the projector, and we can see the colors, the dispersion of that light by this prism. Okay. Usually, in my teaching class, I use many devices. Now I only catch this. Sorry. Okay, that dependence of the wavelength is called the chromatic dispersion. And we can observe that different material has different curves, different chromatic curves of chromatic dispersion. And that is something that we have to consider because, again, the speed of light the speed of light is not the same if you use, for example, blue light, green light, or red light. Another parameter is the absorption. In this case, we can see clearly in the picture, but absorption deals with the fact that the radiation, when comes into atoms or molecules, the radiation sometimes doesn't go out in the same way. I mean, the radiation can be absorbed by the atoms or by molecules, or by, in general by that material. And that is related with absorption. As we listened at the beginning in the previous workshop, the molecules are not symmetric in general. So that asymmetry it can produce absorption, for example, and others effects. So that means that when the electromagnetic waves interacts with these atoms and molecules, the radiation is not. We can see clearly here what the radiation. We hope that the radiation, in an ideal case, the radiation is the same in all the space. But in a reality, the radiation is not symmetrical. Should be more in one dimension, less in other direction. That is it. The fact. Okay, I wrote here that parameters, like the speed, chromatic dispersion, absorption. Now we are going to comment about scattering. Well, how we can understand scattering? We can understand scattering as the emission of radiation in the space. It's not directly related with absorption. It's related with how the initial radiation is re-emitted by the atoms or by molecules. Ideally, in an ideal case, the radiation should be symmetrical, just in a similar way that we have, or in a similar way I described it in absorption. But this scattering is in a real case it's not symmetrical, but refers to the radiation of light. The radiation of light, in this case is scattering, can be described by two theories or by two models. One of them is the Rayleigh theory, by the Rayleigh's theory, or in other case by the Mies theory. Sometimes it's necessary to describe the scattering in that different forms, because the description or the physical description should be more complex. If we use, for example, if we use Mies theory, if we try to use Mies theory to describe all the scattering, we are going to have some problems when we are considering the relationship with the size of the wavelength and the size of the particles. That is the reason, because when we are dealing with small particles compared with the size of the wavelength, when the wavelength is bigger than the size of the particle, it's convenient to use a Rayleigh description. But if we are trying to describe the interaction of light with particles, and in this case, if the wavelength of light is smaller than the size of the particles, it's convenient to use a Mies description. So that's in general the manners to describe scattering. Yes.
Okay. I mean, this is
question.
I'm looking at this.
If I looking at this from a quantum mechanical calculation, should I see these two different regimes?
No, this is classical.
Yeah, exactly. But if I
if I am describing, for example,
My description is not completely quantum mechanical, so I don't use quantum fields.
my description is not completely quantum mechanical. I use a classical description of light.
No, 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 no. This is a physical particle. The interaction, or I am talking about the interaction of light with the size of the particles.
Right. My question is in such a
My question is, in such an equation, should I describe the quantum equation?
should I see in such
Should I see these two
No,
different regimes?
I understand that. No, this is for bigger particles with that
yeah,
size.
because there are for example, Bohr clusters coming to mind. They are not so big. They are maybe a nanometer. And they are described with classical Lie theory.
In that case, I understand that you can use Framing theory. Let me show you this summary. Maybe it will be helpful. For example, if the diameter of particles are smaller than the wavelength, it's convenient to use Rayleigh description. But if you are closer to the size of the particle compared with the wavelength, you can use me, or even more. You can use something more easy that has a right description. Would you have to consider another parameters such as absorption, for example, in this case? I don't know if we.
No, this was good.
Okay. And this is a cartoon how we can see the scattering when the light interacts with a small particle. Yeah, it's more or less uniform. For example, in the large particles, the scatter is not symmetrical. We don't have to be symmetrical. Yes.
I have a question. Why the one condition is the particle should be dielectric?
Okay.
A question from the audience, in which
Because,
case we need to use the particles, dielectric particles.
If it, for example, let me answer in another with another reflection. If we use, for example, metallic particles, we will have to consider another kind of interaction. No, I'm not sure. Well, I don't want to say something that I'm not sure. But we have to consider another kind of physics, another kind of interaction. In this case, for light, we only have to consider, for example, reflection of light, dispersion of light, and that is, I understand that is enough to describe the interaction of light with this kind of particle. But if you use another kind of particle, you have to consider another conditions. Yeah. Okay. Here is a description of that scattering for small particles. Of course, I am describing a general. I am talking about general description. Of course, all these descriptions have has an extended theory, but I am not to explain in this moment. I am not to explain in this moment. Only I want to show you, for example, a description of the intensity that describes that the scattering in a small particle. Maybe this can answer your question, because here in the solution or the intensity that is scattered. We are considering the refractive index that is part of the interaction in this case. What else? Well, maybe that is the most important in this case, the refractive index. And in this case, if we use a metallic or not a dielectric particles, we have to consider 100%. Or maybe the refractive index should be complex or something. This moment, you can answer. Okay. In a brief summary, if the wavelength is large, we have less scatter. And if the wavelength, for example, in our atmosphere, we can imagine what is happening of our atmosphere. And in that case, if the wavelength is large, we have less scattering. That means that we only can observe the orange colors or red colors in the beginning of the day and the sunrise and in the sunset, because well, first because there is more gas, and because the interaction of the wavelength with that molecules is with wavelengths with large wavelengths. And in another case, if the wavelength is short, we have more scattering. That explains why at the middle of the day, we can see the sky in a blue color, because the interaction of molecules is mainly with short wavelengths. So we can see blue with the sky in a blue color. Okay. The next phenomenon is polarization. Okay. We have to say that, for example, this kind of source of light has emitters, many emitters, billions of emitters, small atomic emitters of lights. And in that kind of light, or in this kind of lights, it seems, or in this one, the quantity of emitters for this light are many, so many, billions, maybe. The important thing is that in this case, in this kind of light, each emitter is not synchronized or is not correlated with all emitters. Each emitter that conform this source emits in a different time, in a different direction. So we can imagine that the electromagnetic wave that represents each emitter travels in a different manner, in a different form. So if we try to observe each electromagnetic wave that represents that emitters, we try to observe how is each one. Probably we are going to observe something like this. If we try to, this is the light source. We try to observe what happened with the obviously it's not from home, but if you try to see how is the electromagnetic wave of each emitter, then we can observe that there are many electromagnetic waves represented by the electric field, the oscillation of the electric field. Remember that an electromagnetic wave has two vectors, has two oscillations, an electric oscillation, magnetic oscillation. But in this case, we only represent the electric oscillation. Okay. So In that case, we call, or we can say that this source doesn't have a specific polarization. That means that all the waves doesn't have a specific plane of oscillation. Okay? So we can call natural light, non-polarized light, or aleatory polarization. But what if we can isolate only one of that electromagnetic waves? Or if we have something to order or to put together in only one plane all that electromagnetic waves from a source, maybe one source like this one can give us something that we have. I mean, what if we can obtain a source or we can isolate only one oscillation? Well, maybe we are going to observe the oscillation of one or many electromagnetic waves in this form. If we have that, we can call that linear polarization. And that is something that we can obtain with some devices. Linear polarization. That means that we can control the manner of oscillation of emitters in a source of light. And one of that manner is through a linear polarization. But there are also more ways or more forms to obtain or to control the vibration of the electromagnetic wave. In this case, we can obtain circular polarization. What does that mean? That we can obtain a resulting electric field that represents all the source, and this electric field can rotate in the space or in time, can rotate in a circular manner, in one direction or in another direction. If we obtain that, we call that kind of light, that kind of polarization, we call circular polarization. But even more, we can obtain an arbitrary oscillation of the resulting electric field. In this case, we can obtain elliptical polarization. And the result is that we are going to have an electric field from that source that is rotating but elliptical. Okay? Well, this is important because in many, in several sensors, in several ways to detect parameters, you can use change in polarization. You can detect change of polarization, even in the organic matter. You can detect change in the polarization of light, and that would be useful. Yeah.
In this case, la polarization.
Question from the audience.
How you can relate the intensity.
How to relate the intensity of polarized light and unpolarized light.
The electric field is related to the density of flux. Do you remember the magnitude of the Poynting vector? So when you know the final electric field, or the resulting electric field, you can put that electric field in for example, in the expression of the magnitude of the Poynting vector, and you can obtain the radiation flux.
Another question, quick, more general question. Yeah. So all this phenomenon, the optics, you can relate to the biophotons. Yes. biophotonics something to light interaction with the tissue or biomaterials, right? So how it will be related to the all this phenomenon of optics related to the biophotonics?
Okay. Let me try to answer that at the end of the.
Okay,
Yeah, sure. Let me try to do a summary. Okay. Okay. But how we can obtain linear, circular, or elliptical polarization? Well, there are different physical mechanisms where you can do that. In the nature or in basically in the nature there are several physical mechanisms. One of these is the dichroism or selective absorption. That means that when non-polarized light passes through a material, that kind of material absorbs part of that oscillations and it permits the pass of only one kind of polarization. In this case, linear polarization. So selective absorption or dichroism is something that we can find in some materials in the nature. The other manner to obtain polarization is by reflection. There is a situation where when you launch a light, you can find an angle. You can find an angle where the reflected light is polarized. Scattering the radiation of energy can also produce polarization. In this case, the blue light at the middle of the day is partially polarized. You can observe that if you have a polarization or you have a glass with polarization, you can observe that. And finally, there is the birefringence. Birefringence is something similar to the dichroism, but in this case, there are two axes where the light that passes through that material is polarized. At the end of that material, you can obtain two different linear polarizations. And that's we know at this moment about how to obtain polarization. See, okay. Well, certainly all that I mentioned, all that phenomena, principles, of course, are related with measurements, not only in non-organic material, also in organic material. But the point is that it's not easy. Probably, if we try to see the interaction of light with non-organic materials, should be more easy to understand or to see. But for example, in a tissue, probably many of these effects, we are going to observe many of these effects, but maybe we are going to find that they are mixed and should be not easy to detect, but can be useful to measure some parameters. Okay, I almost finished. There are the two phenomena that we have to consider for biophotonics, or not only for biophotonics in general, in many measurements, is diffraction and interference. In this case, diffraction we can describe reflection, or we can say that reflection is a kind of distortion of an initial wavefront. Well, first of all, diffraction and interference is very related with the wave nature of light. And we can see more clearly in the labs. So diffraction, we can describe diffraction as a distortion, for example, of a wavefront when it passes through a very thin slit or a very narrow hole, very small hole. This picture refers to the diffraction of in water, of waves in water. But it's very similar that as we can see with light, it's very similar. This picture refers to the diffraction of a small aperture when light passes through this small aperture. And again, we can see that kind of distortion around the small hole. We can see rings, brilliant rings, dark rings. That is the effect of distortion. That is the effect of the diffraction of light. But not only we can observe diffraction not only in small slits or holes. We can also observe a diffraction in very sharp borders. For example, in this knife or something like that. We can observe when light passes through the border, we can observe the diffraction phenomenon. And we can distinguish that because we don't have a uniform illumination. We have brilliant fringes, dark fringes, and so on. So that is diffraction. Okay. Let me try to pay attention in this picture. This picture is the intensity profile when light passes through a narrow slit, narrow aperture. If the aperture is very thin compared with the wavelength, probably we are going to observe a uniform intensity in a screen. Let me try to show how is this. How is this? Here we have very narrow slit, and we have a light here coming to through the narrow slit, and then we have a screen here. So what we are going to observe in that case? Well, if the slit, the size of the slit is very thin compared with the wavelength, or less, probably we are going to observe a uniform distribution of intensity in the screen. But if we increase the size of the slit, we are going to observe that kind of intensity distribution. That means that we are going to start to observe not only this brilliant fringe, we are going to observe another fringes. That is, it's happening here in this picture. In this picture. Here we probably have big intensity in the middle, and then we have a small intensity in the sides. Okay. I have to say that because it's very important with the next. So we have a not very thin slit now we have the size of the slit is more or less the wavelength, or even more, is bigger than the wavelength. So we are going to observe this. Okay. Now is more clear. We can see clearly the diffraction. Okay. The distribution of the intensity is not uniform. We can observe different fringes. The brilliant fringes, dark fringes. Okay. Well, now what if we use not only one slit, if we use two, for example. Now we are going to observe this important experiment. The true slit of Young's double slit. That important experiment. The interference in double slits. So here we have to have interference. That means that we are going to observe brilliant fringes and dark fringes. Something like this. But this condition is when the size of the slits are very, very narrow compared with the wavelength. That in this case, this is a theoretical condition, ideal condition, something more real. If you try to develop the double slit experiment in a lab, probably you are going to observe this. We are going to have a mix of diffraction and interference. I think interference is more clear for all of us. Okay. So in the first case, this one, we have interference by a double slit. Here we have diffraction by only one slit. And here we have something more real, that is a mix of interference and diffraction. And what we can see the interference in the inside of the brilliant fringes, and diffraction is the envelopment. Okay, we can see more clearly in the next pictures. Here, for example, if the size of the slit is compared, it is a kind of simulation. The size of the slit is compared with the wavelength. So we are going to have more or less uniform interference, fringes of interference. But if we increase the size of the slit, for example, 5 times wavelength, so we are going to observe both effects, interference and diffraction. Okay. And the question is, and this is useful for what? Okay. First, let me show you. This is again the experiment. What if I cover only one slit? We're going to observe the picture. This picture. Only the diffraction. But if I don't cover one of that slits, if we induce all the light by the 2 slits, we're going to have interference and diffraction. Okay, this is experimental. This is a picture, experimental picture, not my pictures. Unfortunately. Okay. Okay, but what if we launch not only one wavelength? If we launch 2 different wavelengths. For example, if we try to observe the interference pattern with red light, we're going to observe the maximum of diffraction and the other maximums, the secondary maximums of the infraction. But if we change the color, for example, if we use red light, we can observe a similar interference and diffraction pattern, but we can observe that the secondary maximum is not in the same position. It's shifted to the left. This means here. And what if we use blue light? Well, maybe we hope that this secondary maximum will shift here. Okay? And that is that we observe. Okay, first we have a real picture of that here. Here's the maximum. Remember, this is interference and diffraction together. This is diffraction, and fringes inside is interference. And the secondary maximum, the secondary maximums are in different positions. So that is a basic idea to use refracting gratings. That means that you can use many slits. You can use many slits to observe different colors of black light or any kind of light source. You can how do you say? You can separate colors of a light source in this manner. Okay, but if you use few slits, maybe you don't have enough resolution. You have to use many slits. For example, here, if you use more slits, you can see clearly the colors, the separation of colors. So, and that is the reason because this is used for an spectrometer, to develop the spectrometer. Okay. Also, of course, you have to calibrate. First, you have to calibrate to obtain the measurements of the dispersion. Okay. Well, finally, I can finish in this moment with the basics, with the basics in optics. But there should be more. For example, we have to consider, in the case of biophotonics, nonlinear optics. And what is nonlinear optics? Nonlinear optics is beyond these basic principles. Nonlinear optics is allows, as you can see, you can read, allows to change color of light, change its shape and in space and time, and to create shorter pulses of light. So I can say that are new phenomena, new in optics, and they have to deal with high power of light. When we launch high power in over material. One example, and nonlinear optics is now with us. One example is the use of this laser, the green laser. That you can see here, the way of this laser works is because inside there is a small crystal that converts the wavelength from 1064 nanometers to 552 nanometers. That means from infrared to green. And as I mentioned at the beginning, this is not related with electronics, and with well, in this case, not with data science, but is related with health, because we can use this kind of new source of light, or we can see the effect of this new kind of phenomenon in the organic materials, organic matter. So That is because it's important to consider nonlinear optics. And well, we can say something a little bit more about nonlinear optics. Nonlinear optics. We can see that it comes from to consider the inhomogeneous wave equation. In this case, for one dimension, and to solve this equation, we have classically we consider this expression of polarization, where the polarization is directly related with the electric field. But if we are dealing with high powers of energy or high power of light, we have to consider in this expression of polarization, we have to consider more terms in this description of polarization vector. So we can see that we can have a dependence of the second power of the electric field, the third power, or even more. And if we try to solve now this equation, this homogeneous wave equation, with this consideration, well, we are going to predict, and we are going to have more complex equation, a more complex solution, and we are going to observe new effects. Weird effects, if you want to say, but I am not going to talk about that in this moment. But we have more effects that we didn't know when we used low power of light. Well, and even more, at the beginning or in the past workshop, Professor talked about quantum computation, and as I mentioned at the beginning, the next step, next level to understand the interaction of light with matter should be considered quantum phenomena. I mean, to consider the quantification of energy of light with matter. That and that's of course that happens. There are some studies where it is considered pulses of light with high energy, and in that cases, I mean, in the interaction with the organic materials, and in that case, you can consider the light as a particle, as a small package of energy. I understand that, for example, when you try to develop Monte Carlo simulations, you have to consider, in some cases, pulses of light or package of energy, Okay, well, in general, we have radiation. Light is radiation. Light is can describe it in many cases as an electromagnetic wave, and we observe that this electromagnetic wave can interact with matter, and we are going to observe different effects. And in the case of organic materials, we can observe several effects that can be detected, that can be used to measure, for example, a change in glucose, for example, or to change the color of the skin, and that is associated with, for example, a kind of cancer. There are many ways to use light to detect any change in organic material. So tomorrow I'm going to talk a little bit about some experimental, some setups that we have tried in our laboratory in order to use the light in some applications. Well, for me, I think it's all today. Thank you very much. I apologize for my English. I'm not a native speaking of English. I'm trying to do my effort. But okay, thank you.
Questions?
Yo tengo una pregunta. When you talk about circular decoration, we know that sometimes it's used to check if a molecule is of one kind. I am talking about chirality in molecules. Sometimes is we can think in this molecule like the reflection of the molecule. So I know that we use sometimes is used the circular decoration to determine whether one of the both is this molecule. And my question is, do you know if the source of light from the beginning is with circular decoration, or this characteristic from the light is after the interaction with the molecule?
Honestly, I don't work with that effect, but I can comment something. The effect that you have is at the end of the material. Okay. I'm not sure, but probably you have to have you have to know the polarization at the beginning, or the state of polarization. At the end, you are going to observe the change of that polarization, because the molecules are going to change your initial state. But at this moment, I can't say how is the initial polarization. I'm sorry.
Thank you.
Are there any other questions from audience?
Maybe to this one, circular equilibrium. From a computational point of view, the situation is like as if you get an absorption emission spectrum. It's say time-dependent density function theory, and the fundamental difference is the selection rules. So if you have absorption spectra, the selection rules are governed by the electric dipole moment universe. So you have your reference state, and you have your excited state, and you calculate the electric dipole moment between these two states. And depending on the size of this electric dipole moment, that depends the intensities in your spectrum. So, for example, in an infrared spectrum, if you go to circular decreasing, also in the infrared spectrum, in the optical spectrum, these dipole moments are in a square. If you go to circular decreasing, these two moments one is an electric moment and the other one is a magnetic moment. So from this point of view, I think that we circular polarized light from the very first beginning, because the electric and magnetic parts that are separated.
Okay, thank you. Thank you.
Any other questions? Right. Good. So with this, the workshop sections, so we finish for today. So I hope you all enjoyed the keynote lecture in the morning, the quantum computing, also the workshop section on quantum chemistry, and also fundamentals of optics in photonics, for photonics, right? So tomorrow we start the keynote lecture in the morning 8:30. So have a nice evening, and we see you tomorrow 8:30 in the morning. Thank you so much for all the today's participation. Thank you.